Hello everyone, welcome to Neso Academy. We are implementing combinational circuits using VHDL, and in the previous lecture we have implemented the half subtractor using VHDL, and we saw that half subtractor can subtract two single bit binary inputs and generate the outputs difference and borrow. Now, just like a half adder had a limitation, the half subtractor also has a limitation. A half subtractor can only subtract two single bit binary numbers without considering the input borrow from the previous stage and generate the outputs difference and borrow. But in practical digital systems, we often need to perform multi-bit binary subtraction. And in multi-bit binary subtraction, the borrow generated from one stage must be passed to the next stage. But in half subtractor, there is no input terminal to accept this incoming borrow. And to overcome this limitation, we use the full subtractor. So, in this lecture, we will first understand what is a full subtractor, then we will implement it using VHDL. So, our today's topic is full subtractor implementation using VHDL. Now, let's see the definition for full subtractor. A full subtractor is a combinational circuit that subtracts three single-bit binary inputs. Now, just like adders, full subtractor is also a combinational circuit, which means the outputs difference and borrow entirely depends on the three numbers that we are subtracting. And out of these three single-bit binary inputs, the two inputs are the numbers that we are subtracting, and the third input is the input borrow or the incoming borrow from the previous stage. So, what is a full subtractor? Full subtractor is a combinational circuit that subtracts three single-bit binary inputs and it generates two outputs, difference and borrow out. Here, I am representing difference with diff. Difference is the result of subtraction, and here I am representing borrow out with B out. Now, what is borrow out? Borrow out is the final borrow generated during subtraction. Let's quickly understand them. Suppose if I want to subtract a larger number, let's say 1, from a smaller number, let's say 0. So, here we are performing 0 minus 1. Now, for this subtraction, we need to take a borrow. Now, after taking borrow, 0 will become 2 and the subtraction will become 2 minus 1. Now, here 2 minus 1 will give difference as 1, and in this case, borrow will also be 1. So, here difference is 1 and final borrow is equal to 1. Now, suppose if we want to subtract a smaller number from a larger number, example 1 minus 0. Now, here there is no need to take any borrow. So, 1 minus 0 will give difference as 1 and final borrow will be 0. So, I hope you understand what are difference and borrow out. Now, let us look at the truth table of the full subtractor. So, this is the truth table of the full subtractor with three inputs A, B and B in, where B in is the input borrow from the previous stage. And here we are performing A minus B minus B in and generating the two outputs, difference and borrow out. Now, since we are having three inputs, which means we will have 2 to the power 3, which is equal to 8 input combinations. So, these are the 8 input combinations and these are the respective output values for these input combinations. Let's verify the truth table quickly. Consider the first input combination 0, 0, 0. So, here 0 minus 0 will give difference as 0 and there is no need to take any borrow. Now this difference 0 minus this 0 will give final difference as 0 and borrow out will be 0. Now consider the second input combination 0, 0, 1. 0 minus 0 will give difference as 0 and borrow will also be 0. Now this difference 0 minus 1. So here we are subtracting a larger number 1 from a smaller number 0, which means we need a borrow. Therefore, the borrow out will be 1. And after taking borrow, the 0 will become 2 and the subtraction will become 2 minus 1. Now 2 minus 1 will give final difference as 1. Now let's consider the fourth input combination 0, 1, 1. 0 minus 1. Again, we are subtracting a larger number 1 from a smaller number 0, which means we need to take a borrow. Therefore, B out will be 1. And after taking borrow, this 0 will become 2. Now 2 minus 1 will give difference 1. Now this difference 1 minus this 1 will give final difference as 0. Now let's consider the last input combination. So 1 minus 1 will give difference as 0 and borrow will be 0. Now this difference 0 minus 1. Now we all know 0 minus 1 will give final difference as 1 and borrow out will be 1. And similarly, you can verify the remaining input combinations. So, I hope you understand the truth table for the full subtractor. Now, in order to construct the logic diagram of the full subtractor, we need the Boolean expression for the outputs, difference and borrow out. Now, first consider the output difference. For that, look at the rows where output difference is equal to 1. Now here we will consider their minterms. Consider this input combination. Here A is 0, therefore we will take A complement. B is 0, therefore we will take B complement. And B in is equal to 1, therefore we will directly take B in. So the minterm for this combination is A complement, B complement, B in. Similarly, the minterm for the remaining combinations are A complement, B, B in complement, A, B complement, B in complement, A, B, B in. And therefore, the expression for the output difference will be A complement, B complement, B in, or A complement, B, B in complement, or A, B complement, B in complement, or A, B, B in. Now, have you seen this Boolean expression before? Yes, we have already derived the Boolean expression for the output sum in case of full adder. Now, instead of C in, here we are having the input B in. So, in the same way, we will simplify this Boolean expression. So, A complement is common from the first two terms. So, after taking A complement as common, we are left with B complement and B in, or B and B in complement. Or, after taking A as common from the last two terms, we are left with B complement and B in complement, or B and B in. Now, we all know B complement and B in, or B and B in complement is an XOR operation between B and B in. And B complement and B in complement, or B and B in, is an XNOR operation between B and B in, which is equal to complement of B XOR B in. So, the expression will be A complement and B XOR B in, or A and complement of B XOR B in. Now to simplify it further, I will assume B XOR B in as X. Therefore, complement of B XOR B in will be x complement. So, the expression will be a complement and x or a and x complement, which is again an XOR operation between a and x. And here x is equal to b XOR b in. So, the final expression for the output difference is equal to a XOR b XOR b in. Now, in the same way, we can derive the Boolean expression for the output B out by considering the rows where B out is equal to 1. And after simplifying the Boolean expression, we will have B out as A complement and B or complement of A XOR B and B in. So, these are the Boolean expressions for the outputs, difference and borrow out. Now, using these two Boolean expressions, we can construct the logic diagram of the full subtractor. So, this is the logic diagram of the full subtractor. Here we are having the three numbers that we want to subtract: A, B, B in, and the two outputs, difference and borrow out. Let's quickly verify this logic diagram. The output of this XOR gate is A XOR B. Now, this output A XOR B is the input for this XOR gate, and the second input is B in. So, the output of this XOR gate will be A XOR B XOR B in, which is our difference. Now, focus on the borrow out. Here, the first term is A complement and B. And here we can see this NOT gate is performing A complement. Therefore, the output of this AND gate is A complement and B. Similarly, the output of this AND gate is complement of A XOR B and B in. And this OR gate is performing the OR operation between these two outputs. And we are getting our borrow out, which means our logic diagram is correct. Now, let's implement this full subtractor in Vivado using data flow modeling, because we have already derived the Boolean expressions. Therefore, data flow modeling is the most suitable choice. So, let's go to my laptop and implement this full subtractor using data flow modeling. So, we are in Vivado's code editor, and here I'm writing the VHDL code by importing IEEE library along with the standard logic 1164 package from the IEEE library. After library declaration, we have the entity block starting with the keyword entity. And here I am naming the entity as full underscore subtractor because we are implementing full subtractor is port. Now, inside the port declaration, I have declared all three inputs A, B, B in, and the two outputs, difference and borrow out of the full subtractor. And all of them are of standard logic data type. After port declaration, we can end this entity with the keyword end and the name of the entity full underscore subtractor. After entity declaration, we have the architecture block starting with the keyword architecture, and here I am naming this architecture as data flow because we are using data flow modeling code of entity full subtractor is. Now, inside the architecture, after the keyword begin, I will write the two Boolean expressions. Now, what are the two Boolean expressions? Difference is equal to A XOR B XOR B in. And the second Boolean expression, B out is equal to A complement and B or complement of A XOR B and B in. So, inside the architecture, I will write the first expression. Difference is assigned as A space XOR space B. Now we all know why I am using this space. So Vivado can easily detect this XOR operator. B space XOR space B in semicolon to end the statement. Similarly, I will write the second Boolean expression. B out is assigned as. Now in B out, we are performing the OR operation between the two terms. Therefore, I will write these two terms separately inside the parenthesis. So, the first parenthesis OR operation with the second parenthesis. Now, in the first parenthesis, I will write the first term, which is A complement and B. And to perform A complement, I will use the NOT operator. And to make it look clean, I will write NOT of A inside the parenthesis. Then we will perform the AND operation with B. Now, in the second parenthesis, I will write the second term, which is equal to complement of A XOR B and B in. Now, we all know complement of A XOR B is equal to A XOR B. So, I will directly use the XOR operator. So, I will first write A XOR B inside the parenthesis, A XOR B. Then we will perform the AND operation with the third input B in, semicolon to end the statement. So, this is the data flow modeling code for the full subtractor. Now, first let me save this project. And after saving this project, let's see the schematic diagram generated by Vivado. For that, go to RTL Analysis, click on Open Elaborated Design and select Schematic. So, this is the schematic diagram generated by Vivado. Here we are having the three inputs or the three numbers that we want to subtract. A, B, B in, and the two outputs, difference and borrow out. Now these two XOR gates are used to generate the output difference. The output of this XOR gate is A XOR B, and the output of this XOR gate is A XOR B XOR B in, which is our difference. Now for the borrow out, look at this AND gate. Here, this bubble is representing the complement. So the output of this AND gate is A complement and B, which is our first term. Now for the second term, look at this AND gate. This AND gate is generating the output A XOR B and B in, which is our second term. And this OR gate is performing the OR operation between these two outputs and generating the final output, which is our borrow out. So, Vivado directly converts the data flow modeling code into the logic diagram. So, I hope you understand this RTL schematic generated by Vivado. Now, let's see the simulation waveforms to verify our VHDL code. For that, go to Simulation, click on Run Simulation and select Run Behavioral Simulation. We all know simulation waveforms will verify whether our code is correct or not. So, this is our simulation waveform window. Here we are having our three inputs A, B, B in and the two outputs difference and borrow out. Now, I have already explained how to assign the input values by using force constant as well as by using force clock. So, let me quickly assign all the 8 input combinations so we can verify our VHDL code. Here, I have assigned all the 8 input combinations and we have generated the waveforms. Let me maximize them. Let me zoom in further. Now let's verify the same 4 input combinations that we have verified in our presentation. The first input combination, here we are performing 0 minus 0 minus 0, and we are getting difference as 0 and borrow out as 0, which is correct. The second input combination, here we are performing 0 minus 0 minus 1, and we are getting difference as 1 and borrow as 1, which is absolutely correct. Now, the fourth input combination, here we are performing 0 minus 1 minus 1, and we are getting difference as 0 and borrow out as 1, which is correct. And the last input combination, here we are performing 1 minus 1 minus 1, and we are getting difference as 1 and borrow out as 1, which is correct. So, these simulation waveforms verify that our VHDL code is correct. So, I hope you understand the data flow modeling code for the full subtractor along with its schematic and the simulation waveforms. So, we have implemented the full subtractor in Vivado using data flow modeling. With that, we are done with the topic of full subtractor using VHDL, which means we are done with this lecture. I will see you in the next one. Thank you.